Another thing to check is about the assumption that we made that errors are normally distributed. Okay. Yeah, so we check the normality of the error as that's one of our assumptions for the simple linear regression. To assess this, we look at a normal probability plot or a normal QQ plot of the standardized residual. So this plot would have ordered standardized residuals on the vertical axis. So ordered standardized residual on Y, and expected order statistics from a standard normal distribution on the horizontal axis. Well, you'll see the example of this QQ plot real quick. And the way we evaluate the QQ plot is that if this is close to a straight line, then the data are said to be consistent with that from a normal. If not, we have evidence of non-normality. A very quick example here. So this is QQ plot is for our corrected Ch3 bound data set. So that's after we remove this 3 flower bound data points and then refit the data. And I plot, well, by R, we plot the normal QQ plot, and looking at here, well, the theoretical quantiles from negative to 2 and the standardized residual from the from our model is like from negative 3 to 2, which is not really aligned with this negative 2 to 2. And also this dashed line is theoretically where it should be if it follows normal distribution, like the standard residuals follows normal, it will look like this dashed line. But the data we have is like, it's not really along the straight line. So we can see that, we can see that this, we have evidence is not like really normal distributed for the standard residual. So this linearity of the model is not, the linearity of this data point is that not that great from just looking at here. They're off quite a bit. A quick R note, this previous one plot, I modified the previous slide, but forgot here. I'll correct this when I post the slides. So the previous plots are this one, normal QQ plot. It's from R. If you do plots of the whatever name you use for the LM object when you run the function LM, and it will show you 4 of those. Well, I didn't copy the first one because we do not really use it that much. It's actually used to look at if the residuals is it have, are they like randomly distributed? Are they have constant variance, but which will also can be tell from this third plot, which we'll talk about this a bit more later. For now, just focus on this one for the QQ plot to look at if it's normally distributed, if the error is normally distributed. And the fourth one is handy to look to check the Cook's distance. Well, this dash, the red line is the cutoff for Cook's distance. If it's like beyond this 1, beyond this 0.5, that means they are they have high leverage. So this is what the force plot telling you. Well, I'm just telling you this for checking plots. You can easily get it by doing this plot of your LM object. And we'll talk about this third one, about the constant variance a bit more here. Again, we always refer back to the assumptions that we made for the regression, is that we have L, I, and E representing the 4 assumptions. Well, E means the equal variance, that is corresponding to the constant variance. Here we are checking. So saying the errors have constant variance, equal variance. So we'll discuss the method for checking this assumption. And if you find there will be non-constant variance, we'll discuss 2 different ways to deal with it. Either we do transformations or we do a weighted least squares, which we'll cover in the next chapter for the transformations at least. So if your data has non-constant variance and you ignore it, you are invalidating all the inferential tool we've been using, such as the p-value, confidence interval, prediction intervals. So all of this will not be valid. So this is an important thing to check. I have a new example here. Let's just go through it. Your company wants to submit a big contract to clean corporate offices. You have data for a sample of 53 different days of how many crews were used and the number of rooms those crews cleaned. So your data points n equal to 53. And here is this data set. You want to model the relationship between the number of rooms and the number of crews. Basically, we want to predict the number of rooms that can be cleaned by 4 crews and 16 crews. So build a linear model and do prediction. And this is what the data looks like. And this line shows you the linear regression model. I show you this like the summary of your model here. And Y is the number of room cleaned, and X being the number of cleaned crews, cleaning crews, sorry. We will refer back to this. Okay, I put them on the same slides. So the prediction based on this model by using predict, like the interval, like the argument for interval equals to predict, you will get the prediction interval for this new data. And we'll talk about that. And okay, let's start from the beginning. How do we check the model? So the first one is well, actually this is the third one when you do the plot, your LM object. But this is the standardized residual and plot versus this X. So by looking at here, if you like focus on the trend, the band of this, of the variance, like how wide your residuals span along when you increase the number of residuals, you will see kind of a funnel shape, right? It's kind of increasing as you increase the number of crews. So in this way, we can tell our assumption of the constant variance is well related. So this funnel shape is the evidence that the error has non-constant variance. This is what you will get from R. It shows you the square root of the standardized residuals. Well, and many statisticians have recommended use the standardized residual instead of this residual. That's why I showed you there. We have this residuals plotted here, and we have this square root of the standard residuals also plot here when you do this plot object. Most people look at this one. They think this is this one is more proper to look at. And we also talked about like if we look at residuals directly, it has problem being the variance of the residual is actually non-constant because it's related to the leverage of the data points, if you recall. So, well, in this case, we plotted the square root of the standardized residual, and we can easily see that there is a positive trend, and it goes up as we increase the number of crews. So that's again the evidence of non-constant error variance. Well, we can actually calculate the empirical standard deviation, because in this example, we have discrete x values. So x value is being the number of crews. So we can calculate for each of them what the standard error looks like. Well, by the actual calculation, we can see there is a trend. It's increasing as we increase the number of crews. This end here is the data points we have for those different number of crews. Number of points means the number of days. If you look at the data point, the data set we have is for each day, the number of crews and the number of room cleaned. So yeah, this is just give you the number of data points. Each of this different value of number of crews. But anyway, this is just to show you, if you calculate the standard deviation, it clearly tells you the variance are not constant. Well, again, the forward diagnosis plot in R, well, in this case, you might be curious if you plot this forward diagnostic plots. This residual and the standard residuals, they are the same. They look the same, but if you look at the y-axis, the vertical axis, the range are different. And the pattern, they look very much the same is because the fitted value are just a function of x values. So the shape of the plot will be the same as the previous plot. The bottom left is similar to the previous plot. So this is the reason if you are curious about it. Okay, so yeah, we would have to have some strategies when we see this non-constant variance. The first one is we can use the weighted least square to account for the changing variance. This is in the next chapter. And try a second approach you can take is try and transform the data so that you can remove this non-constant variance. Before you fit the model, you make the variance constant, and then fit your model. And we'll discuss this next week. So again, just recap, we mentioned this in the very beginning, like the general steps to diagnose your regression model. You need to determine if the model is valid. Typically, you just make a plot of the standardized residuals, or in R, we do the square roots of the standardized residuals, which is also okay. Determine which data points have X values that has a large effect on the estimated model, which is called leverage point. And once we get leverage point, we determine if they are good or bad by looking at if they're outlier or not. How do we deal with leverage points? Two different approaches. And also examine if the assumption of constant variance is reasonable, by checking if there is a funnel shape of the error variance, and also pay attention to correlative data. So that will violate the assumption of that error being independent to each other. Well, if the data is collected over time, then time from time they are correlated, so they are no longer independent. So that's a clear evaluation of our assumption. And if your data size is small and you want to do prediction intervals, and you'd better check the normal assumption if the error are normally distributed, but if by looking at the QQ plot. But if the data size is big, so normally it should be okay. But it's always good to check. So again, this is the general steps or all the aspects you need to consider when you're trying to evaluate your regression model. And this, if the model is, whether a model is valid or not, will determine your accuracy when you do the inferences. But if this, if all the assumptions are not met and you do the inferences, then they will be nonsense. So this is important to do before you really do the inference. Okay, that's it.